which will be presented to you by our CEO, or rather our head of education, which is Steve, and then our electrical engineering lecturer, which is Samukelo. So we'll be hearing from them throughout the presentation. And just a little bit of information with regards to the presentation. Can you please just to reduce our interruptions and so forth, could you please just switch off the notifications for now, and then you can switch them back on afterwards. Also, I'd like to just turn your attention to our Q&A box, but for those of you that don't have the latest Teams, you might not have that, but you are welcome to use the chat box to type in your questions for later. We will be taking questions, so you're welcome to type in your questions for Steve and Samkelo on the chat box if you do not have the Q&A function. So with that being said, just to give you a little bit of information about this presentation, you will get a copy of the slides after this, and then you will also have a certificate of attendance, which I will put on the screen at the end of this presentation. Okay. And then just to give you some information about ECT. ECT is relatively new. However, we are an engineering specialist affiliated to EIT, which is the Engineering Institute of Technology. That's headquartered in Australia, and obviously this is all made possible by our industry-driven programs, which offer world-class accredited education, and that's all thanks to our lecturers and our instructors. So what makes us different is our unique delivery model. So later on, you will hear about that and how that works, but currently, we do have to go through this, which is basically the conduct for this webinar. And if you post things that are not permitted, you'll either be removed, or in future, you'll not be allowed to attend any of our webinars. Unfortunately, these are the policies for ECT. And today's topic is lightning, earthing, and surge protection. Like I had mentioned earlier on, it will be presented by Steve Mackay, which is our ECT and EIT managing principal, as well as Samkelo Nene, which is our ECST electrical engineering lecturer. So they will be taking over from now. Steve, if you'd like to, you can take the control of the presentation from your side.
Thank you so much, Kumo. Can you hear me okay?
Yes, perfect, thanks.
Excellent, fantastic. So I'll introduce myself and we'll introduce my colleague and anyone else in a few seconds. The first thing is, says my microphone's been disabled. Just want to make sure we don't lose anyone. Are you going to change the slides, Kumo?
Yeah, sure, I can do that for you on my side.
Yeah, because it doesn't allow me to change the slides here at the moment. Oh, it says take control.
Yes, you can take control.
Request. It says your camera has been disabled. Doesn't allow me to run the slides here.
Yeah, no worries. I can do it from my side.
If you could, yeah. So when I go like this to my nose, can you just change the slides?
Sure. No
Thank
worries.
you very much. It means I don't have to say, please change the slides, because we get a bit tired of it. Thank you very much. Okay, my name's Steve Mackay, and I'm obviously very keen about entrepreneurship and engineering, and obviously lightning and earthing is something which I've had to do over the past few years. So I thought we'd just do a quick presentation on this, and hopefully we'll have a few comments from all my colleagues here. Welcome. And if I just disappear, it's because I've dropped out. I'm actually in our Johannesburg campus today, hopefully next week back in Perth, Western Australia, and then shortly after that back in the UK. So I get around a bit. So I'm very curious about learning, and hopefully you can all hear me. So first thing is, can I ask all my colleagues listening, can you please put in the box there, can you hear me, yes or no? Just text in the boxes so we know how the box works. Yes or no? Yes, excellent. Okay, fantastic. Thank you very much. Okay, so really, that's brilliant. Okay, fantastic. Okay, so my good colleague Samkelo Nene is going to also present. He's one of our very active instructors in South Africa, and he's highly enthusiastic about electrical engineering. And Samkelo, over to you. Can you do a short introduction to who you are? He's going to co-present some of the stuff with me. Thank you very much, Samkelo.
Thank you, Steve. Good day, everyone. My name is Samkelo Nene. As Steve has already introduced my name, I am based here in Johannesburg, and today I'm here to present along Steve. Yes, thank you.
Excellent. Thank you. Carry on, Samkelo. Oh, sorry, one back. Sorry, yep.
Okay, so my background is in heavy current, which is power engineering, and I formerly tutored and also facilitated labs at the Durban University of Technology. And in my previous contract before ECST, I was with the South African National Energy Development Institute, supporting the recent G20. So I look forward to today's discussions.
Thanks very much, Samkelo. Brilliant. Okay, so Samkelo will jump in and interrupt me on occasion to create some entertainment and liveliness for all of you. And also he's going to do a short presentation on the issues of, should we say, earthing halfway through this presentation. So thanks very much for joining us, Samkelo. So really what we're going to do today is quick objective, lightning and surges. I want to really spend most of the presentation on that. And then some protection principles against lightning. There's a lot of, should we say, magic principles that are used by various people which don't quite work or are worth the money, which I hope to highlight with a few controversial slides. So please forgive me. Hopefully we'll have a few entertaining disagreements. And then I'd like to then talk about a topic which is very close to my heart, which is introduction to earthing, grounding. In North America, we tend to refer to grounding rather than earthing, whereas in Europe and Africa and Australia, we use the word earthing, and grounding has a slightly different context, so I'll be referring to both. And then there's a few case studies on earthing from Sydney, and that's in New South Wales, Australia. I won't go into those, but I thought I'd just add them in at the end of the presentation, just to bring up a few points I'd like to highlight. Unfortunately, we don't have time to go through 80 or 90 slides because I suppose Kuma wants to go home eventually. so we don't want to keep talking forever. And there's halfway through, there's a few questions for you to answer, and hopefully you'll be able to answer them in the quiz in the box, just to make it a bit more interesting. And then finally, I'll finish off with a conclusion, just to try and type a few points. So really, lightning and transient surges are a big issue, and there are some easy fixes and then there's some more difficult fixes. So I just want to quickly, obviously, highlight those, and then finally talk a bit about earthing design and some protection strategies. So just to basically get your brain thinking. Unfortunately, there's 60 or 70 slides. As you would know, in 45 minutes, not going to happen that we're going to go through every slide. but hopefully they'll be a useful reference for you in the future. And we'll obviously make those available after the presentation. So let's go for it. So first thing is lightning and surges. There's a wonderful lightning storm. And I was just wondering, Kumo, do you think there'll be a lightning storm tonight in Johannesburg? It's a bit gloomy, so hopefully there will be. I don't know
These
what you
days
think.
I wish I could tell because it's this weather's so unpredictable, but I don't know.
You used to be able to set your watch at 5 o'clock by the thunderstorm coming up. Anyway, Johannesburg is particularly malevolent with lightning and thunder, and this is a copy of one of those storms picture. So the next thing is, this is a sort of space-based optical sensor, and you can sort of see the level of flashes. If you look at this graph here, you'll see that right in Central Africa, huge problem with thunderstorms near the equator. If you look towards Johannesburg, down in the southern part of Africa, you'll see a bit of lightning activity. And obviously, another reason, if you go and look at North America, if you go and look there, you'll see that reddish area. That's Florida. Florida is particularly bad with lightning storms. And then Australia, if you look at Australia, towards the west there, you'll see in the northern part of Australia, Darwin, a very humid area, lots of lightning there as well. And then, of course, Malaysia, Singapore, northern Indonesia, right in the middle, obviously a lot. So it's quite an interesting chart there. But as Kumo says, the weather is changing, so who knows what the future lies. This is 10 years old, this chart. And here's a particular one of Australia, and you'll get charts of every country, and that shows you the malevolence of lightning. Again, if you look at this chart here, average annual thunder day map of Australia. And again, you'll see Perth, where I come from, is fairly low. It's on the left of the map. And then as you move to the northern part here, towards Darwin, it gets pretty malevolent. So if you look at the northern part there, it's pretty heavy lightning activity. And you'll see the number of days of lightning, probably 60 to 80 days a year, which is quite significant, whereas Perth is probably 5 to 10. And believe me, I know all about lightning because our Labrador dog goes berserk when the lightning, probably a few hours before the lightning starts, she immediately knows something's happening and then tries to go underneath the bed. So I know all about it. But certainly, you can see Northern Australia, huge problem. Southern part, not so much of an issue. So these charts exist for every country. If you just go back, and obviously, you may start by saying, hey, mate, the chance of being hit by lightning is 0. If you look at this chart here, and it's pretty up to date, this chart, if you look there in Australia, to take an example, 6 to 10 people are killed each year. Now, Australia is uber safe, very, very safe. And you'll find that most common causes are playing golf, swimming, sailing, fishing, being in large open areas. So 6 to 10 is quite a significant amount, you know, when you think about how safe Australia is. But you'll see smoking, 1 in 400 chance if you do 10 cigarettes a day. Drowning, 1 in 30,000. And of course, struck by lightning, 1 in 2 million chance. So there's a very low probability of lightning hitting you. So why do you think we're so focused on lightning when we should be spending more money on combating smoking? Can you put a text in the box there? Let me ask my chum, Samkela, what do you think? Samkela, what's your opinion? Why are we so focused on lightning when we could be talking about smoking? Sorry to ask you an awkward question.
It's okay. I'll also try to respond, because remember, lightning, as much as it could be severe to the human life or hazardous, it also affects the systems, electrical system, from our power grids to electronics. So we have to also take that in context.
Thank you very, very much, Thank you very, very much, Samkelo. Absolutely right. I agree with you 100%. I'm sorry to put you on the spot there. I'm always asking random questions. But as Samkelo says, one of the worst things happens here in Johannesburg. If you haven't done lightning protection, you come in the next morning, your computer system's completely blown apart because you haven't got protection for lightning if you've got copper cable connection. So the catastrophic impact on your electronic systems is pretty severe. So obviously it's something you got to be concerned about. And I think most of the comments there seem to indicate that. Thank you very much, everyone commenting. I'm just trying to see why I can't see the comments on the side there. Meeting chat. It's on this in the middle here, there's comments, but on the chat there's nothing.
This is also pretty new to me. I'm not sure.
Yeah, there's comments there. Why is it not on this side here? About Madam S. Thanks.
I do see them below
Yeah,
the
but it
presentation.
doesn't matter, doesn't it? It's fun. Yeah, I should have won. Okay, no, thank you very much for everyone's comments. I've got two sets of screens here for comments. So absolutely, as everyone says, protect buildings. Thank you, Hezbollah, Mazur. Roy Beard, Wilmot. Smoking is a choice. Lightning is not a choice. That's very good. Thank you very much for that touch of humor. Lightning is uncontrollable. Absolutely right. And we should be able to control lightning. So this is obviously quite important. And obviously, lightning is quite devastating when you see it. I always find it really awkward. I was in the Drakensberg Mountains last week, and there was a lightning storm, and I'll talk about the duration, the time gap, about 10 kilometers away. And I saw the trees, and I thought I should go under the tree. But of course, I always say, do not go under the tree because that's more likely to be hit than you being out in the open. But let's talk about that in a tick. So the next point is there are a few myths about lightning. So let's just talk about some of the myths of lightning, which I always find quite amusing. Lightning never strikes twice. Well, we've been told these myths till we, for most of our lives. But unfortunately, lightning hits the Empire State Building on the same spot 25 times a year. I mean, what can you say? So lightning, unfortunately, does come back to the same point. The other little myth is rubber tires will insulate me from lightning. Believe me, when lightning is been, it doesn't suddenly do a detour around your car because you've got rubber tires. Unfortunately, no go. It'll hit the car. So that's a bit of a myth. And there's a few others there. I'm not going to get bogged down on them. You should never touch anyone being hit by lightning. Unfortunately, with electricity, if they've been electrocuted, do not touch them. Use a wooden or insulator to try and get them detached from the electrical connection. But unfortunately, lightning is very quick and there's no problem trying to get the person off to the hospital. Lightning can be prevented. No, there's always these myths about you have this radioactive sort of stuff going into space from little connectors on the roof and that'll detract the lightning. Complete rubbish. And obviously, the new high-tech types of lightning rods can control lightning. Again, very hard, many of them, to justify. I'm always open to new suggestions, but very hard to justify much of that advertising. Some probably true, but a lot of it's not quite correct. So let's move on to the next one. So there's quite a few myths about lightning, and hopefully I can put that out of everyone's mind. There's a localized nature of lightning. You can see it's very localized. The bolt from the blue, you can see there, look at that. The lightning in this picture should go straight down, but it's gone horizontal for a while, then it's gone down at about a 30, 40 degree angle. So it's very, very unpredictable, bolt from the blue phenomenon. So really, lightning is very random. It's very hard to predict. And I'm not aware of any cost-effective lightning system which gives you 100% protection. Maybe 95%, 99%, but very hard to get 100%. And there's also very difficult getting an early warning system providing 100% first strike warning. There's always a bit of a percentage there. So just bear it in mind. And here, this is a horrific picture. Here's the space shuttle about to take off. Beautiful picture. And of course, guess what the lighting does? You would have expected to hit the top of the shuttle or the top of the tower, but it's gone right around the corner. Again, totally unpredictable. So at this stage, short of AI coming to the rescue, it's probably not easy to predict it. So that's really important to realize. And there are lightning detectors out. Here's a particular one. You know, you can probably get some indication of the direction and also the sort of distance away. But again, there's quite an element of risk there. So Boltec doesn't necessarily. So when is lightning an immediate threat? And this says 5 kilometers is 1768. And by the way, this is now, I've quoted a standard which is out of date. I've quoted the older standard, but 5 kilometers, probably a little bit optimistic. When you hear lightning, the thunder, then you need to take cover, and that'll be more than 5 Ks. So really 8 kilometers, 10 kilometers or more. And the 30-30 rule is a really important rule. And that means that if you think about lightning, the speed of sound travels at about roughly, please don't shoot me down here, at about 300 meters a second. 300 meters a second. So in other words, in 3 seconds, it transmits over about a kilometer distance. 3 times 300 is about 900 meters, almost a kilometer. So you can say in 3 seconds, it's gone through a kilometer. So the 30-30 rule is important. 30 seconds gives you about 30 times 0.3, which gives you about 9 and a bit kilometers away, or as we put in that sketch there, 10 kilometers. So really, that's when you need to be wary of lightning, 10 kilometers or 30 seconds, which is quite a distance away. And you can theoretically hear up to 13 kilometers. Obviously, if you're in a noisy city or there's some other activities going on, you're in a very noisy ocean, you probably won't hear more than 5 or 6 kilometers, but you should be able to hear up to 13 kilometers. And the only real safety is buildings or fully metal enclosed vehicles, large metal sheds. Unfortunately, when you're out in the open, you see a tree, that's not necessarily a good idea, unfortunately, much as it's very tempting. And the other point to make is that when the lightning bolt hits, that's also not only problem you face. There is a arc of electrical shock that penetrates from there up to 40 meters from where the thing, so you can get, shocked up to 40 meters from when the lightning hits the ground. So it's quite hazardous if you really think about it. But the 30-30 rule is quite a useful rule, and I believe it's still used. Sorry, Kumar, to make you change the slides all the time. It's just the joy of Teams. But we will be changing to big blue button in due course, so the problem goes away. So here's a rather distressed golfer. The lightning's hit the ground, and you can see how it's gone off. Lightning discharge current, so it's hit the ground, and it's also gone off the green into different locations. So or up to 30, 40 meters away from that, you've got potential risk. Okay, so let's talk a bit about the protection principles against lightning. And while I'm getting ready to talk about this. Let me ask my colleague, Samkelo, are there any points you would like to make with that? Any additions, or do you disagree with anything I say, Samkelo? Hopefully you do.
Not as yet, Steve. Not as yet.
Thank you very much, Samkelo. And okay, so really what I want to just talk about now is some protection principles against lightning. And I also want to talk about some of the magic that people are sold on that will protect you from lightning, which perhaps isn't necessarily guaranteed to work. So I just want to, so all I want everyone here to do is think critically. And then that's really important. So we're going to talk about air terminals, earthing and bonding, surge protection, safety procedures. So I just want to talk a bit about that. Really protection principles. Unfortunately, time is always tight. Now, here are some shots, pictures. Unfortunately, I cannot mention where they're taken, otherwise we'll have the pantsuit off us. So they are various locations where the client has allowed us to take pictures of a particular mining site. And really, the client called us in to do some consultancy work, or in fact called Kobus Strauss, the guy that I've used the slides from, and I acknowledge at the end of the presentation, he kindly gave me these pictures. And they're quite actually educational because they're a real thing. So there, if you look at this is a mining site. I think it's a gold mine, actually. Now, if you look there, you'll see right in the middle of the picture. Can you see that spiky bit there? Now, the client has been advised by a firm of consultants to protect his installation. So he's going to spend a whole lot of money, or she's going to spend money on this air terminal, hopefully to nail the lightning. Of course, complete waste of money, complete waste of money. There's no real benefit there, unfortunately, because the lightning will go around it. So look, it may hit the terminal, but it's not necessarily guaranteed. So not necessarily a good call there. Let's look at another one. Here's another one. Air terminal on top of metal structures. I'm a little bit perhaps pejorative here, a bit prescriptive here, and it's not incorrect. It's just not necessarily going to protect the building from lightning, unfortunately. So spending this money may not actually get you a return. That's all we're saying. So it's not incorrect, but it's probably not a good call. So again, you'll see right in the middle of the picture, a little pole, again, to hit the lightning, to hit that. Unfortunately, lightning may go to the right or left or hit the structure. So
Steve?
Yeah.
I would then ask you then, what would you then propose? Would you propose to have maybe on the edges?
Yep, no, some
around.
No, you make a good point there, and thank you for raising it. I would say the best thing that you can do here is take the metal structure, tie it all together, so it's all conductive, and then make sure that has a really good earthing connection into the ground right at the bottom there. Because if lightning hits that roof, let it go straight down to the bottom, and I would say that would be a better solution. I don't think the poles, individual poles, are likely to be hit. So it's probably not necessarily a good call. That's the best. So that's the thing. Now here's another view, and this picture is a little bit difficult to see, but if you look at this picture, you'll see a whole heap of lightning air terminals all over, all on top of metal structures. Again, probably not going to be that successful. Again, take the metal structure and put in some sort of earthing for the metal structure itself. Whether the pole gets hit, not necessarily things. Okay, so Hendra says there, do you use IEC 62305? Yeah, that's the latest standard, I believe. So, yep. So what I'm saying is there's some concerns. Now, the next slide is another interesting one. Now, when you're putting a lightning earth conductor in, here's an interesting one. Can you look at that? Can anyone see what they've done there? What they've done is they've got the earthing conductor, which is great, brilliant. But what they've done there, can anyone tell me what the problem is with this picture here? it looks like the guy or lady that's done the job here, they've coiled up the cable so that they can extend it if they need to in future. But what has happened with that coil? What has it done as far as a lightning conductor is concerned? What is that coil? Just go back. Yeah. What has that coil done? Loop. Yeah, loop. Thank you very much. Talis, thank you so much. Absolutely right. Increased impedance. Yeah, absolutely. Impedance is enemy number one. So you've got a huge inductance there. So that would actually be a major problem. So whoever did the audit of this site didn't check that. And this is a real world installation. Look, very nice to have that extended cable because you may need to use it. I understand that 100%. So this is very awkward to say, well, no, it's probably not a good idea because it's going to have a huge inductance. So absolutely right. Thank you very much. So that gives you extra impedance or resistance to a AC alternating current. So big issue. Okay, now here's another example. Here's a surge arrestor. But the problem with this surge arrestor is put in there, but there's no earth connection. It hasn't been earthed adequately. So again, whoever checked the site should have looked for that. So this is a surge arrestor trying to avoid a problem. Yeah. Thanks, Mr. Turner or Mrs. Turner. RD Turner, thank you very much. LDIDT is the voltage that you'll develop across the inductance. Yep. Again, another problem here. So, earthing is really important. It's done correctly. And because it only happens occasionally that you get hit, no one really picks this up. So these are all issues that we've picked up by auditing. Now, here's another one. Now, again, the surge arrestor earthing introduces surges again to the wiring. Unfortunately, my screen's very small because of this Teams that we're using. I can't really see it, but basically what's happened here with this particular diagram, if you look in that junction box, the in and out cables have all been mixed up. So basically you'll get a surge coming through to the surge arrestor, but unfortunately the surge will be induced into the other cables as well. So again, one has to be really, really vigilant about how one wires this up. Again, it's reintroducing surges into the wiring. So again, very important to go and audit these processes afterwards. Here again, now look at the top of this surge arrest. The surge arrest is all brilliant. Thank you very much. That's fabulous to put those in. But they've gone and mixed all the cable up. So basically the in and out cable of the surge arrestor all mixed up. So of course the one cable will reintroduce the surge into the other. So again, mate, you need to check this out. I'm very disappointed with this. So very important there. Again, same problem here. So it's a real art to do the right thing here. And I just wanted to counsel you, all of you, to be very vigilant here and about the installations that have been done. These are real world installations. And because the lightning strike will happen once every 3 or 4 years, probably no one picks this up. But if you're going to do a proper job, check. And also, I suppose, follow my rule with engineering. And some color, I have a few rules in engineering. First of all, I have the KISS principle. Can you tell me what the KISS principle is? KSS? KISS principle? Can you tell? Yeah, thank you very much, Isaiah. Thank you very much. Bingo, KISS principle. So keep it simple, stupid. So everything should be done simplistically and simple. That's obviously a very important engineering principle. The other principle I have is when there's any doubt, there is no doubt. When there's any doubt, there's no doubt. So if you've got any doubt about whether this has been done correctly, there's no doubt it's a complete stuff up. So watch out for that as well. Very good engineering principle. Samkela, do you think those are good principles or do you think they're rubbish?
Let's hear from the audience.
I'm not an engineer, but that sounds like some good life advice as well.
Thank you very much. I'm delighted I've got some support here. Thank you very much. Yeah, Isaiah is quite right. The KISS principle is a critical part. So when I teach my undergrad students electrical circuits, I do the KISS principle, and when there's any doubt, there's no doubt, and we use it for some of the design work. But it's all important stuff. Thank you very much, everyone. So those are important rules. Unfortunately, time is tight. We're running out of time, and I really apologize for slipping behind here. And now here's an example of a plane hit by lightning. And now whenever I'm traveling in a plane and there's lightning around, I'm always a bit nervous, bang, bang, bang. But, the planes are all being designed so that the lightning will go along the surface and then carry on downwards. And I always love this picture here. It's a plane over Dallas or something, but it's really important thing is. Oh, sorry, Tadas, I'm so sorry. Sorry, please forgive me. You won't see any lightning. I know that at all, so don't worry about it. So, okay, so what we want to do is just talk a bit about earthing and grounding. Unfortunately, there's not much time, but I've created a few case studies, which one of my colleagues did a few years ago in Sydney, which would be really worth, I'll just mention them at the end, but I just want to just talk about earthing and grounding. And then my good colleague, Samkela, will just do a few words about that as well. And obviously, earthing and grounding is really important. And there's obviously it's got to be practical, easy to construct, maintainable, and cost effective. So let's just talk a bit about earthing and grounding to protect us and resistivity. Okay, so over to you, my good friend, Samkelo.
Yes. I'm not sure if you're able to take control.
Just Kuma will change the slide for you when you want it.
Okay. I think I'll let him know then. So as Steve did mention at the beginning, we tend to use these words interchangeably, grounding and earthing, and also the West tend to stick to one, and then the global north and the rest of us tend to stick to another. But it's understandable, because if you were to define to ground, or grounding is to establish a connection to earth, and earthing, earth is earth. So it's easy to use them interchangeably. But just to clarify on that, grounding is connecting all the live parts of an equipment to earth. So these parts, they will carry currents under normal conditions. So the neutral part, if we were to speak about maybe the neutral conductors or the grounded phase conductors, and as whereas rather when it comes to earthing, is connecting the metallic parts of the equipment to earthing. So these parts, they wouldn't carry current under normal conditions. So grounding is more about the protection of the oral system or the equipment, whereas earthing is primarily about the protection of the workers, of the human life, or to avoid hazards to human life. And we see here on the slide, this person is drilling whatever into the wall, and there's a fault in the drill. So this could be perhaps, maybe there's an insulation failure of the wires inside the grid, and perhaps one of the wires is exposed and gets in contact with the casing, which would then cause a fault. And if the electrical outlets, even the drills, sometimes you'll find that drills will have prongs or pins, and also that electrical circuits will have to be earthed properly to then redirect that fault to the ground. But if it's not, then however comes in contact with that casing, then be the part to the ground due to the potential difference. We can move on to the following slides. Thank you. And one of the examples that we can look into is the transformers. If we were to think of a connection of a three-phase phase transformer, if we were to once again compare the two, if we were to let's say there's a fault in the transformer. So normally under normal condition, you'll find that there is zero current flowing through the neutral point of the transformer. And then under fault current, you find that the three phases they become unbalanced. So in this case, or in such a case, then the fault current will go through the neutral point to bring about the balance back to the system. So the system is protected, and that is grounding essentially, as where, let's say there is a fault in the transformer, and then the flow of current then also flows through the casing. Should someone get in touch or touch the transformer, then they'll provide there will be that path to the ground, as you see on the example, the person that is in contact with the transformer. So proper earthing is very, very important, because if the transformer, for this example, it was properly earthed, then even if the person touches the transformer, they won't be shocked because there's already earthing to the ground. And also one of the important things when it comes to earthing is the excess termination rod or the earth rods. So they have to be of high grade electrolytic copper to provide that conductive part. I saw someone did mention of the IEC standard, the 6305, and I think it's also the IEC 62561, which speaks of the types of rod that it has to be conductive, and also its inner core of the high steel of the high strength steel has to be strong enough to be able to be driven to the ground. Yeah, so I'll hand it back to Steve.
Thanks, Samkela. Thank you very much for your words of wisdom there. Really appreciate it. So really, obviously, earthing requires a specific design process. Some of those points Samkela's mentioned. Obviously, if you're putting earth rods into the ground, you need to watch out for the soil resistivity. So there's a few slides here devoted to the soil resistivity, working out what that is, and you need a plan. So I've put that in the case study. So we'll quickly mention that, but that's quite difficult to come up with the right number, because it does vary quite a bit. So, oops. Next slide. Yeah, so soil resistivity is a key factor. And obviously, one of the challenges is when you're measuring the soil resistivity, because you want to try and make sure that when you put an earth rod into the ground, it's as low as possible. But obviously, if the ground is wet, it'll have a low resistivity. And when it's in the middle of drought, summer or winter, when there's no rain, then it's dry again. So it is a challenge. Or if you try and put an earth rod in on a rock face, again, what's the resistivity going to be like? So it can change quite dramatically. So obviously, one has to look at the worst case scenario when you're doing this. So the resistance of electrode is the resistance of the metal, copper, contact resistance, and then the resistance of the soil, the resistivity. One of the funny things which people find quite surprising is when you put the rod into the ground, if you increase the impedance of the rod, so it's bigger and bigger, it actually doesn't really impact much. It's actually the depth of the rod in the ground. So increasing diameter rod doesn't reduce resistance. That's not quite correct. It does, but it's not a big impact. Doubling the length of the rod reduces the resistance quite significantly. So that's quite important, and obviously putting multiple parallel. So earth can dissipate high currents for short durations. Obviously, you could have serious heating and vaporization effects as well, smoking, and there's a calculation on the smoking current there. that root, that calculation is slightly wrong. There should be a bracket around the root rho times T. But anyway, it's just to show you that there can be some heating issues. So when you're looking at a substation, and you'll see crushed rock. Why would they have crushed rock over the surface of soil within a substation grid area where it's got good earthing? Question for you. Thanks, Tadas and his bulla. The increase in impedance, absolutely right. Thank you. Avoid direct contact with earth, but it's high impedance. That's really important. So thank you very much, guys. I'll have to move on, unfortunately. So crushed rock provides high resistance, or resistance is probably the wrong word. The word that you've used there is impedance to reduce the hazard from a step potential. So granite rock, and the funny thing is granite rock, even when it's wet, is actually still got a fairly high impedance. And that's why it's good if you've got a rock ground and you're trying to put a earth rod in, very hard to get a good result. So there's various soil resistivity test methods. I'm not going to go through them all here, but the first one is the two types here. This is the Wenner method, and you can see there basically what you're trying to do with this, and the Schlumberger method is the other one. The Wenner method there, as you can see, you've got you've got a voltage V in the middle and you've got I on the outside. So the trick is that you look at the I, it injects the current into the ground. So you've got a current that you inject, and then the V is where you measure the voltage. So you've got earth stakes, you've got 4 earth stakes there, and V is where you measure the voltage. And then from that, obviously, V equals IR, R equals V over I. You can work out what the R is, so that's quite useful. There's another technique there as well. Unfortunately, time is tight, so I'm not going to go through those. When you're looking at the soil resistivity test plan, dial before you dig, very important. Site survey is very important. And of course, what you can do now, which is used quite extensively, is using radar systems to go and look at the surface. So you have a ground radar, ground penetrating radar, which goes through and tells you what's underneath as well. That's quite useful now, and because it does generally work. Geotechnical data, meteorological data. So there's 3 case studies here. Unfortunately, I'm not going to go into them in depth because we've now run out of time. Sorry about that. But let's go to the next slide. Now, here's a question here. What is transferred earth potential and how does one deal with it at a substation? Can you tell me what that is? Any takers there? It's a little bit off center, this question, by the way, but still, it's worth talking about. Here's Buller, you really know what you're talking about here. Yeah, step and touch potential. Yep. Yeah, some fellow was talking about step and touch early on. Yeah, so you're right. So really with the transfer potential, earth potential, EPR is earth potential rise, and can be transferred to a non-fault location if you've got a metal pipe going through the site. So obviously use ground mats and isolation transformers. Otherwise, you'll find that you're connecting to remote sites. So there's 3 case studies here. I'm not going to go through them, but I just want to point out a few points here. Just if you can just flick through them. Yeah, so there's 3 case studies which I put in the final thing here. And I just want to point out a few points with them. Just go on. This is just the plots. Yeah, so just go back. Yeah, so what I would like to point out is when you're doing a soil resistivity test, before you do your earthing installation of your rods, you need to check what's going on. So be wary of taking measurements and then going back to the office to calibrate, to check them out, because you may find that you have to do weather tests a few times more, and you may do it in one line there, then you may want to do one perpendicular as well. And you may need to be very wary about the weather. In other words, in the middle of summer, it may be extremely dry, and you doing all your earth resistivity tests during winter when it's very wet, when the resistivity is brilliant, it's low. So you need to be wary. In fact, I had another thing I had, and as I said, please forgive me running out of time here, but I had one particular problem up in the northern part of Australia. I said to the contractor, I said, have you done the earth stakes? Mate, I'm doing the test for the earth stakes. Don't worry, it's all under control. And he said to me, I have to do the test at 10. I'm going to do the earth resistivity test at 10 o'clock tomorrow morning. So I said, what? He said, no, 10 o'clock in the morning is when I do the test. I said, really? Why didn't you do it in the afternoon? No, mate, we've got to do it in the morning at 10 o'clock. And I found out to my horror that we were right on the beach. And he was doing the earth resistivity tests when it was high tide, when the resistivity was very low. At 4 o'clock in the afternoon, it was horrendously high resistivity. So, you know, you've got to be very wary about these things. Soil drying can be a problem. So never take any chances there. Final point here, why is galvanic corrosion a problem for electrodes and how does one deal with it? This is one of the last questions, guys. What's galvanic corrosion? So Uluwasian says, what's the best time to test resistivity? Check the weather and make sure you test it when it's really the worst case scenario, dry, dry, dry. That's what you've got to test. Don't test it when it's wet. What's galvanic corrosion? Any suggestions there? Okay, so galvanic corrosion could be a problem for electrodes. And the suggestion here is it's caused by electrically connected to similar metals to form a galvanic cell. So if you use copper, which is what we normally use, guys, for your electrodes, they can seriously damage underground structures such as iron or steel that are electrically connected because you get corrosion. So you get your iron or steel corroded, so be wary. So you may need to use some other metal for your rods. Copper is always the best choice, but watch out for corrosion. Okay, last few slides here. I'm getting a bit of pressure here to finish. Yeah. Just go back there. So one of the just go to the conclusion. Sorry, Como. Yeah, just one other point with the resistivity tests. Watch out for installed copper cables, steel cables underground. They may reduce the resistivity, and you've got to be really wary about anything else installed. Or there may be an electrical installation nearby which would cause distortions to what you're measuring. So there's a whole art form there. And I'm going to do a presentation of resistivity in the next few months and a detailed presentation. So it's just to give you a few pointers. So comprehensive test plan, try and do all your analysis and testing on site. Don't go back to the office because you may need to do more testing, and make use of other available data, look at the weather patterns, and then obviously plot the data doing the measurements to see what exactly is going on. Okay, that's all from me. Any comments from my good colleague, Samkela?
No, Steve, thank you.
Thank you very much. Is there anything you disagree with me there?
No, but I do
I'm
see
sorry to
that
hear that.
there are questions on the chat.
Yeah.
They were asking
Any
about
comments?
the
Thanks.
best material. Would you?
Thank you very much, Samkela. Yeah, so hopefully you've all got a little bit of a thing there. And I've got I've taken the first two sections. First one is Kubert Strauss, used to be a very good instructor of ours. He's a really knowledgeable fellow in earthing. And then Rodney Urban of ACON, which is a big consultancy firm. He did a really good presentation at a conference we ran on earthing. He's very knowledgeable. And those last two slides came from him. So there you go. Okay, thank you very much, one and all. Any comments, questions, suggestions before we call it quits?
Yeah, so we are left with 5 minutes. So maybe if you guys could give us some questions, and then we can then head over to where I'll give you guys the link for the certificate of attendance, as well as make sure that you guys understand when the slides will be sent to you guys. So if you guys have questions, you may go ahead and just type them in the chat box or in the Q&A.
Okay, there's a comment there, instrument to be used for testing, Fluke. Just use Fluke or looking for equivalent to a Fluke. Fluke is the gold Rolls-Royce one. Obviously, you may not want to use that. You may want to use something cheaper, but there's a huge number on the market. Fluke's probably the gold one as far as I remember. Fluke is what I've used in my diagrams here, but that's just one of the more expensive ones. Any chance to share details of source for lightning risk process? Yes, we can certainly add that into the presentation. I'll add that in, Dinesh. Do you think you could pull something together on that? We'll pull something together on the lightning risk assessment. I will. We've got a whole course lasting 3 months on this topic. So I'll steal some materials out of that, and I will quote you on that. So, Samkela, can I ask you to get hold of the certificate course on lightning? If you ask,
so we do have a few that I can just.
Yeah, we've got a whole 3-month course, a certificate course on that topic, and I've tried to do it in 45 minutes.
Let me just.
I've been a bit aggressive with compressing it, but we've got some good stuff there. So let's send out an extract from those materials to Dinesh and co here.
Yeah, sure. So, I can, at the end of the presentation, I'll pop in the links for the courses with regards to lightning protection.
And we can give them some extract from those materials as well. There's a comment there: best materials and equipotential bonding in wind turbines. Very, very good question. Samkela, let's see if it's in that as well. It should be in that, but let's find out.
And then it
says your lightning course is on hold now. No, it shouldn't be. Is our lightning course on hold? Shouldn't. Oh, I'll check. It should be running. There's a whole lightning course here. In fact, it's got remote labs as well, and but I'm not promoting the lightning course. I'm just saying. How many semesters is electrical engineering degree? It's a 3-year degree, and it's 6 semesters. Sorry.
With the option, that's Kumo. With the option, depending on your schedule at work or whatever may be going on at that time, you've got the option to select your modules, and therefore we then can extend the course to 6 years. That's for the bachelor, so to speak. And then similarly with our masters, you also have the same option with the selection of the modules and how long you'd be taking it for. Sorry, Steve, for interrupting. You can.
No, sorry, Kumar. Now I'm being a bit bizarre, a bit deranged. Sorry, apologise for that. But certainly the courses you can run at your own pace. It's really important to have a routine, though, to study. Don't try and do too much, and obviously try and have a routine. My best routine is 5 o'clock in the morning till 6 or 7, and then a few hours on the weekends. I love studying new stuff because, as you can see from my grey hair, I've got a lot to learn. But thank you, Kumar, and I really appreciate you jumping in there and doing all those extra comments. Samkela, thank you so much for adding value to my rather boring presentation. Hopefully, thank God I didn't get found out by anyone asking a too awkward question, but thank you very much, one and all. Really appreciate it. I look forward to presenting again. Samkela is going to be doing some presentations as well. So thank you very, very, very much. Really wonderful to be here today. And thanks for all your awkward questions. Really appreciate it. Thank you, Kumar. Thank you.
Thank you, Stephen. Thank you,
Thank you,
Samkelo. This
everyone.
was very insightful, and I found this to be so interesting.
Thank
And I myself am not an engineer, but we did have a question about what's the difference between online and face-to-face study. Is it the same duration to the study for? Yes, there is not much of a difference except the fact that with face-to-face, it's a standard 3-year course for the bachelor, and then in terms of online, that's where you've got the option to select your modules and how many you'll be taking for each particular semester. So that's probably the only difference, and the fact that our on-campus courses, which is face-to-face, are offered in Australia. Any more questions? Okay, I can pop in just because of the Teams, the way it's functioning today, I will pop the link as well as the links for the course for the professional certificate. I'll pop it on the chat just shortly after I close it. You will still have access to this chat, so you can copy the links. Samkela, thank you for your time, and to all our attendees, thank you for attending. We do appreciate your time, and all the best with your endeavors. Thank you so much, and enjoy the rest of your day.
Thank you, sure.